Hello, this is our recording for the simulation of the problem for the CP101-1L finals. Given a problem of designing a sequential circuit using JK flip-flops that detects prime numbers from the input lines, if the input is x equals 0, y equals 0, the state transition is 0, 0 to 1, 1 to 1, 0 to 0, 1, and then back again to 0, 0. If the input is x equals 0, y equals 1, the state transition is 0, 0, where the following next state is the inverse of the present state, and then back again to whatever the present state was. If x equals 1, y equals 0, the state transition is 0, 0 to 0, 1 to 1, 1 to 1, 0, and then back again to 0, 0. If x equals 1, y equals 1, the state transition is 0, 0 to 1, 0 to 1, 1 to 0, 1, and then back again to 0, 0. Includes state table, state diagram, flip-flop input equations, and logical diagram in the solutions. From that problem, we derive this state diagram, where as you can see, let's take for example current state 0, 0 with an input of 0, 0 as well. It moves to 1, 1, and then to 1, 0, to 0, 1, and then back to 0, 0. And as you can see, the output for every single one of those transitions is 0, as 0, 0 or min term 0 is not a prime number. Now let's take for example 1, 0 with an input of 1, 0 as well. As we can see, at 1, 0 it goes to, from 1, 0 we go to 0, 0 to 0, 1 to 1, 1, and then back to 1, 0, all with having an output of 1. And then we derive this state table using that. And then as we can see, z here is only 1 whenever x and y is equal to 1, 0 or 1, 1, or mean terms 2 and 3, which are the only two prime numbers in a 2-bit input, while flip-flop inputs JA, KA, JB, and KB were simply based on the excitation table for JK flip-flops based on current states A, next state A, current state B, and next state B, respectively. So with that, we derived this circuit, and through k-mapping, we derived to the input flip-flop input equations of JA is equals to B x nor x y naught plus x naught y, Ka is equals to x naught y plus b x nor y, Jb is equals to x naught plus a x nor y, Kb is equals to x naught plus a x or y, and z is simply z, or the output of each transition is simply equal to input x. Now starting with Ja, output B is placed into an XNOR gate with the ANDed value of input x and the inverted input y. The value of that is then placed into an OR gate with the uh, inverted input x and input y to produce the input for JA. To produce the input for the J input for the A flip-flop. Next, for the K input, it is x naught y, which is the inverse of x with input y, or with input b as output b rather as well. uh, Output b XORed with input y. Both of those are placed into the OR gate, and then output of that is placed into the input k of flip-flop A. Next is input j of flip-flop B, or JB, is equals to inverted x over here, inverted x, ORed with the XNOR of A and Y. So output A is placed into an XNOR gate with input y, and then the value of that is fed to an OR gate with the inverse of x, and then fed into input j for flip-flop B. Now for input k, it is x naught plus a x or y Therefore, in the XOR gate, it's output A, input Y, and the value of that is fed into an OR gate with inverted X, and then fed in value of that is fed into K input of flip-flop B, and then simply output Z over here is simply connected to input X. Now for the simulation. It can also be observed that our circuit has three other switches. S1 and S2 are used for setting the value of these two flip-flops to 1, while reset is for setting both res is for resetting both values to 0. This will allow us to set an initial state for each flip-flop without having to transition to each states based on the state diagram, which will take up more time. So for now, at the start of the simulation, let's say we have an initial state of 0, 0 for A and B, and 0, 0 for external inputs X and Y. As you can see, Z is not on, as 0, 0 or midterm 0 is not a prime number. 0, 0 moves to 1, 1, 1, 0, 0, 1, and back again to 0, 0. As you can see, through all that time, in output Z remained 0. Now let's say we move to input 0, 1 or midterm 1, wherein initial state is still 0, 0. Now Z is still not on, as input 0, 1 or midterm 1 is not a prime, and from 0, 0 it moved to 1, 1, the inverse of 0, 0, back into 0, 0, and repeating this infinitely until we change the input. Now let's say we change the initial state to say 0, 1, i.e. B is equals to 1, A is equals to 0. For now, let it run for a second to allow B to have an initial state of 1, and there. Now let's input 0, 1, and as we can see, from 0, 1 it went into 1, 0, back to 0, 1, repeating infinitely until we change the inputs. Now next, let's do 1, 0 with an initial state of 0, 0. Now Z is now on, as 1, 0 or midterm 2 is a prime, and then from 0, 0 it moved into 0, 1, 1, 1, 1, 0, and finally back to 0, 0. Now let's say we have 1 and 1 at an initial state of 0, 0 once again, and Z is on because midterm 1, 1 or midterm 3 is a prime. From 0, 0 we move to 1, 0, to 1, 1, to 0, 1, and lastly back to 0, 0. Now let's say that we change the inputs in the middle of the run. Let's say for now let's have here at 1, 0. Let's say we change the input to 0, 1, which would invert it to rather we currently have a current state of 1, 0 with if we place the inputs at 0, 1, it would invert this current state into 0, 1 as well. So as you can see, Z was turned off because it is no longer a prime, and then the state was then inverted into 0, 1. Now let's say from here, once again 1, 0. Let's say we have an input of 0, 0, which should give us 0, 1 as well. Let's see, correct. And then let's say we move into an input of 1, 0 from a state of 0, 1, which should give us 1, 1. And Z is turned on as input 1, 0 is a prime, and it moved into 1, 1. So it's correct. Thank you, and that is the end of our simulation.